Hello, my name is Koty Creel, and I am a student in AST301. I'm going to give a presentation on the Nobel Prize in Physics, presented in 2019 to Michelle Mayor and Didier Queloz for their first detection of an exoplanet. So what is an exoplanet? Exoplanets are planets that have formed outside of our solar system, orbiting other stars. While exoplanets can orbit a variety of stars, including pulsars, most are known to orbit stars like our sun. These strange worlds have been found in many different forms. Some of them look like the planets within our solar system, and the others are dramatically different. 15 types of exoplanets are currently listed in the Unified Astronomy Thesaurus. Five of the exoplanet types refer only to size. In order from smallest to biggest, they are rocky or terrestrial planets, super Earths, mini Neptunes, ice giants, and gas giants. And they can be divided into multiple subcategories, such as planets in the super Earth and mini Neptune size. Those range may be ocean planets, having liquid water oceans hundreds of kilometers deep. Some rocky planets found in carbon-rich systems may be carbon planets, having rocks formed from compounds of silicon and carbon, different from our solar system's silicon and oxygen rocks. Hot Jupiters and hot Neptunes are big gassy planets with fast orbits very close to their stars, so close they'd be tidally locked, with a hot hemisphere permanently facing the star and a cold hemisphere permanently facing out. There are cold Jupiters and cold Neptunes as well, orbiting further out, just like the planets they're named after. Lava planets are large and superdense worlds in close hot orbits. And pulsar planets, like I mentioned before, orbit pulsar stars within their intense magnetic fields. And of course, what we are really searching for are habitable planets. Habitable planets are Earth-sized ones that orbit a distance from their star where liquid water could be stable, meaning they could be habitable to life as we know it under the right circumstances. Every star has a habitable zone and a range of distances in which surface liquid water could be stable. Astronomers using NASA's Spitzer Space Telescope and ground-based telescopes have confirmed that this system shown here, TRAPPIST-1, has 7 rocky planets. 3 of these planets are in the theoretical habitable zone, the area around the star where rocky planets are most likely to hold liquid water. So how did we come to realize that all of these strange, not so new worlds existed? And how are we able to not only know they are there when we can't see them, but also how can we know so much about them? Well, in 1995, Swiss scientists Michel Mayor and Didier Queloz announced the first detection of an exoplanet. The planet, 51 Pegasi b, is located 50 light years from Earth and is a gas giant known as a hot Jupiter. It orbits its star every 4 days at 8 million kilometers away from the star, with a temperature of over 1,000 degrees. The discovery of an exoplanet orbiting a solar-type star began a revolution in astronomy. Since Mayor and Kalos detection, more than 4,000 exoplanets were discovered by the time they were both awarded the 2019 Nobel Prize in Physics for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos. And these bizarre new worlds are still being discovered in a large variety of sizes and compositions. Mayor and Kalo challenged our preconceived ideas of planetary systems and forced scientists to revise their theories of the physical processes of planetary formation. The discovery of 51 Pegasi b utilizing the LED spectrograph revolutionized astronomy and initiated an entirely new field, with new instruments focused on finding and characterizing exoplanets. Mayor and Kalo were instrumental in developing the radial velocity technique that is still being used to search for exoplanets today. The radial velocity method for detecting exoplanets relies on the fact that a star does not remain completely stationary when it is orbited by a planet. The star moves in a small circle or ellipse, responding to the gravitational tug of a planet. When viewed from a distance, such as from Earth, these slight movements affect the star's normal light spectrum. Usually, highly sensitive spectrographs, scientists can track a star spectrum, searching for periodic shifts in spectral wobbles. The spectrum appears blue shifted and then red shifted. If these shifts repeat at fixed intervals of time, then it is almost certainly caused by an exoplanet orbiting the star. And here is a radial velocity graph of 51 Pegasi that Mayor and Kalo used to confirm an exoplanet orbiting the star. The wobble of the star is presented here as peaks and troughs, or dips on the graph. Each of the individual points shown here are actual measurements taken and shows the changes in wavelength as the star wobbles back and forth from the gravitational tug of the planet. So I'm going to demonstrate this here with the simulation provided by the Nobel Prize Museum. And here you see the bottom edge with the moon above to the left. So this is Earth down here, and the moon right here. And right above Earth, you can see the constellation Pegasus. In this rectangular part of the constellation, a small star is visible. Hold on. So right here, we can only really see this star if it's really dark out. This is 51 Pegasi, where Mayor and Kalo discovered their exoplanet. So I'm going to zoom in on 51 Pegasi, and we can see the exoplanet orbiting around the star. We also see how the star follows a small orbit. This is because it is affected by the gravitational force of the planet, and the planet and the star rotate around the common center of gravity, probably somewhere around here. This creates an observable wobble as the star is moving back and forth in the direction of our line of sight. The speed at which a star wobbles can be measured as its radial velocity, and since it affects the wavelength of the light beams that we are looking at. So even if we cannot see the planet directly, we know it must be there. This is similar to the Doppler effect, which occurs when a sound source is moving towards or away from us. When the star is moving towards us, we can see the wavelength become shorter and the light becomes bluer. And when it's moving away from us, we can see the wavelength becomes longer and the light is redder. Okay. So as I just mentioned in the demonstration, the changes in color can be precisely determined by measuring the star's light's wavelengths, providing a direct measurement of its velocity in the line of sight. The amount of change is determined by this formula that tells us that the observed wavelength of light changes depending on the relative velocity between the source and the observer. If the source is moving away from the observer, positive v, the observed wavelength will be longer or redshifted. If the source is moving towards the observer, negative v, the observed wavelength will be shorter or blue shifted. Since the radial velocities are extremely low, astronomers measure thousands of wavelengths simultaneously at the same time using a spectrograph. The radial velocity is usually measured using the observed Doppler shift of spectral lines given by this formula, which indicates that the change in the wavelength of light is proportional to the relative velocity of the source of the observer, divided by the speed of light. This equation expresses how the wavelength of light shifts due to the relative motion between the source and the observer. This is a simplified way to understand the Doppler effect for light, where the motion of the source causes a shift in the observed wavelength. Radial velocity is not the only method being used to discover exoplanets today. For example, the transit method utilizes photometry to search for exoplanets by measuring the intensity of a star's light when a planet passes in front of it while within our line of sight. This is similar to what we experience during a solar eclipse when the moon passes in front of the sun. These methods can be even used together. While the radial velocity method provides the mass of the exoplanet, the transit method provides the size or radius of the exoplanet. With these parameters together, we can calculate the exoplanet's density, thus measuring its structure and composition. Transit photometry also allows astronomers to observe the exoplanet's atmosphere as the light from the star passes through it. Other methods being used to discover exoplanets are direct imaging, microlensing, astrometry, and the timing variation method, which actually tells us a second exoplanet is there. And here's an example of the direct imaging method. And you can see as they place a coronagraph over the sun or the star, the host star, the light is reflected off of the planet. So there. And since the first discovery of an exoplanet orbiting a solar type star, new planetary systems are not only being discovered by telescopes on Earth, but also from satellites. TESS has discovered 7,351 potential exoplanet candidates, with 570 confirmed. And prior to TESS, the Kepler Space Telescope discovered more than 2,600 exoplanets. Today, James Webb Space Telescope is actively confirming exoplanets and determining their atmospheric compositions, and there are more to be confirmed after the launch of the Nancy Grace Roman Telescope in 2027. Ground-based telescopes have also helped confirm and characterize exoplanets. They work with space-based telescopes to provide details of exoplanet atmospheres, composition, and other vital statistics. And here is an example of an exoplanet that is being researched by scientists utilizing the James Webb Space Telescope. Here you can see the confirmation of WASP-39b using the transit method, which, as I mentioned, allows them to also observe the planet's atmosphere with this transmission spectrum here in the bottom image. The spectrum shows clear evidence for water and carbon dioxide and a variation in temperature between the morning and evening on the exoplanet. The blue and yellow lines are the best fit model that considers the data, the known properties of WASP-39b, and its star-like size, mass, temperature, and assumed characteristics of the atmosphere. There are also a multitude of citizen science projects today, increasing the number of confirmed planets and our understanding of planetary formation. By assisting expensive space telescopes like James Webb Space Telescope with continuous ground observations to maintain the orbital parameters that would otherwise become stale or inaccurate over time. Here is a light curve that I created in a research program at ASU, research topics in exoplanets with Professor Molly Simon and Heather Hewitt. We also used the transit method, and you can see the dip in brightness shown here as the exoplanet is orbiting in front of its star. The data provided by this light curve allows us to provide updated and accurate orbital parameters so that space telescopes do not waste crucial time waiting for transit or even worse, missing the transit. The discovery of an exoplanet orbiting the solar type of star began a revolution in astronomy. Since Mayor and Kalow's detection, more than 4,000 exoplanets were discovered by the time they were both awarded the 2019 Nobel Prize in Physics for their contributions to our understanding of the evolution of the universe and Earth's place in the cosmos. And with these planetary worlds still being discovered in a multitude of sizes and forms, we may eventually find an answer to the question of whether extraterrestrial life exists. Thank you.